When the cosmos chooses to surprise us, it rarely does so quietly. Instead, it delivers a spectacle that forces us to question everything we thought we understood. The discovery of 3I Atlas, confirmed in July 2025, is exactly such a spectacle. Our third verified interstellar visitor, and by far the most puzzling one yet. For decades, astronomers have prided themselves on predicting cometary behavior with near-perfect accuracy: an icy nucleus, sunlight warming its surface, jets of gas and dust venting into space, and a predictable shift in trajectory caused by that venting. 3I Atlas, however, refuses to follow that familiar script. Larger than expected, heavier than predicted, chemically unusual, and astonishingly resistant to motion even when its own jets are firing, it has quickly earned the label of a cosmic anomaly. The story began on July 1st, 2025, when the Atlas survey in Chile flagged an object racing across the sky on a hyperbolic orbit. That detail alone set it apart. Only 2 other visitors had ever been confirmed to come from beyond our solar system: Oumuamua in 2017 and 2I Borisov in 2019, but while Oumuamua was a faint, enigmatic shard and Borisov resembled a more ordinary comet, 3I Atlas has combined brightness, activity, and longevity in a way that gives us a rare chance to study it in detail. Early measurements suggested a nucleus roughly 5.6 kilometers wide, already larger than Borisov and placing it in the same size class as the more massive, long-period comets native to our solar system. Yet in this case, sheer size is not the headline. The real shock lies in its motion. Ordinary comets are not passive travelers. As sunlight heats their surfaces, sublimating ice creates outgassing that works like tiny thrusters, nudging them off purely gravitational paths. In Oumuamua, a tiny extra acceleration sparked years of debate about whether it was a comet at all. Borisov, in contrast, behaved exactly as the textbooks predicted. But 3I Atlas has flipped the pattern upside down. Despite being visibly active with a coma, jets, and a dust tail, its trajectory has deviated from a purely gravitational path by only a minuscule amount, less than about 15 meters per day squared. That is far smaller than expected, given the amount of gas and dust pouring from its surface. Physics tells us something simple but profound. If the thrust is real and the motion is barely changing, the object must have enormous mass. By balancing the visible activity against the near absence of acceleration, astronomers estimate that 3I Atlas carries a nucleus mass exceeding tens of billions of tons, making it several orders of magnitude heavier than either Oumuamua or Borisov. It is not the largest comet ever recorded. Bernardinelli Bernstein still holds that title, but for an interstellar comet, 3I Atlas is a giant among wanderers, and that raises uncomfortable questions. If the galaxy's debris field follows the expected pattern, many tiny bodies and only a few giants, then why did our third visitor turn out to be such a heavyweight? Have our surveys missed a hidden population of smaller objects? Or does nature itself scatter larger fragments more easily than we assumed? That is why astronomers describe 3I Atlas as an anomaly, not because it defies natural law, but because it challenges our prior expectations. It is a living contradiction, a reminder that the universe is not obligated to play by our rules, and that every interstellar visitor is a chance to rewrite what we think we know. If its sheer weight and stubborn trajectory were not strange enough, the chemistry of 3I Atlas adds yet another layer of mystery. Most comets in our solar system display a familiar balance. Water vapor dominates, with smaller amounts of carbon dioxide and carbon monoxide contributing to their activity. But in the case of 3I Atlas, early observations from the James Webb Space Telescope have revealed a coma unusually rich in carbon dioxide, with CO2 levels overwhelming water vapor to an extent rarely, if ever, seen before. This immediately places the comet at the extreme edge of known cometary behavior. In simple terms, it looks chemically off-center, as if it were born in an environment very different from that of our own solar system. Even more intriguing is that ultraviolet instruments have picked up clear signals of water vapor well beyond the distance where comets usually remain dormant. Normally, significant water outgassing doesn't occur until a comet has approached relatively close to the sun. Yet 3I Atlas seems to have been active much farther out, suggesting that either its surface layers are unusually porous or that it harbors volatile compounds behaving differently than expected. Such early activity makes this interstellar object stand out from every comet studied before. The peculiarities don't end there. Polarimetric measurements, the way sunlight scatters off its dust. Particles show patterns that do not align with either typical cometary grains or asteroid dust. This could mean that the dust grains in 3I Atlas have unusual structures or porosity, essentially tiny fingerprints pointing back to a birth environment distinct from the one that shaped our solar system's comets. If confirmed, these differences could serve as a direct sample of conditions inside another stellar nursery, frozen and carried across interstellar space for billions of years before arriving here. And then comes perhaps the strangest hint of all. Early spectroscopic data suggesting the presence of nickel without the usual companion, of iron. In cosmic chemistry, nickel and iron are almost always found together, forged in the same stellar furnaces and bound in similar compounds. To see one without the other would be highly unusual. Astronomers are careful, though this signal may still be a calibration error or a data artifact. But if it turns out to be real, it could mark a radical departure from what we know about planetary chemistry. Either way, it has already prompted a wave of scrutiny and debate across the astronomical community. Put these threads together and a picture begins to form. A comet that is big, heavy, and chemically peculiar. It behaves like a comet in many ways. It vents, it glows, it builds a tail, but at the same time, it breaks rules that we thought were universal. For some, this sparks speculation about whether all natural explanations will be enough. For most, including NASA's leading comet specialists, the answer is more grounded. It still looks and acts like a comet, just one that challenges the boundaries of what we thought comets could be. And that tension between anomaly and normality is what makes 3I Atlas one of the most exciting cosmic visitors of our time, as if its unusual weight and chemistry were not enough. 3I Atlas is now stepping onto the stage of cosmic experiments in real time. In late September 2025, space weather forecasters predicted that a coronal mass ejection, CME, a massive burst of solar plasma, launched from the sun, would sweep directly across the comet's projected path. Such encounters are rare even for ordinary comets, and none has ever been documented for an interstellar visitor. For astronomers, this was an unexpected but golden opportunity, a chance to see how a comet from another star system responds to the raw fury of our sun comet. Tails are delicate structures, easily disturbed by changes in the solar wind. In 2007, for example, a CME famously severed the ion tail of comet Inca, creating the dramatic image of a tail being cut away like by a cosmic blade. Scientists hoped to see something similar with 3I Atlas if the CME hit at the right time. Its ion tail could snap, bend, or even disconnect entirely. These changes aren't just beautiful to watch. They act as natural probes of the surrounding plasma environment, revealing the density, speed, and turbulence of the charged particles rushing through interplanetary space. To catch such an event on an interstellar comet would be historic, adding space weather physics to the already fascinating story of 3I Atlas. But the most highly anticipated milestone came just days later, on October 3rd, 2025, when the comet made its closest approach to Mars. From Earth, the distance was still immense, millions of kilometers, but for spacecraft orbiting Mars, this was an extraordinary opportunity. Instruments aboard the Mars Reconnaissance Orbiter, especially the high-resolution HiRISE camera, were tasked with capturing detailed images of the comet's coma and jets. Meanwhile, other spacecraft, MAVEN, the European Trace Gas Orbiter, and even China's Tianwen-1, could train their instruments on the passing visitor, collecting spectra and data from angles impossible to achieve from Earth. These observations were not expected to reveal surface detail. The comet's nucleus was still far too distant for that, but they could constrain some of the most unknowns: the size distribution of dust grains, the geometry of the jets, the chemical species venting into space, and perhaps even the comet's rotation. In effect, Mars served as a unique outpost for studying an interstellar body, turning the red planet into a front row observatory for a once-in-a-lifetime event. Once the Mars flyby was complete, another challenge awaited: solar conjunction. As 3 Atlas slipped behind the sun from Earth's perspective, our direct view was cut off for several weeks. During this time, astronomers would rely on space-based telescopes positioned away from Earth's line of sight to keep the data stream alive. Then, by December 2025, the comet was expected to re-emerge, likely brighter than ever, with its coma at peak activity and its tail stretched by weeks of solar heating. At that point, the astronomical community planned a full campaign. The Vera Rubin Observatory would track its broad motion, night after night, while Webb and other telescopes dissected its spectrum for rare isotopes and chemical signatures. For scientists, this sequence of events, CME impact, Mars flyby, solar conjunction, and December reemergence turned 3 Atlas from a curiosity into a living experiment, unfolding step by step. Each stage promised answers, but also raised new questions. Could its tail truly be severed and rebuilt under the force of solar storms? Would Mars-based instruments detect something our Earth-based telescopes missed? And most importantly, would its unusual chemistry and stubborn mass continue to defy the rules? In many ways, the comet itself had become less of a mystery and more of a laboratory, an interstellar experiment running across the solar system, with every instrument humanity could muster aimed at unraveling its secrets. By December 2025, after weeks hidden behind the glare of the sun, 3I Atlas was expected to return to view in a spectacle more dazzling than before. As the comet emerged, its coma, already energized by solar heating, was predicted to expand dramatically, pushing its apparent size to hundreds of thousands of kilometers. For astronomers, this was the long-awaited prime observing window, the moment when the interstellar traveler would finally display its full character against the dark canvas of the night sky. Ground-based observatories mobilized on a global scale. The Vera Rubin Observatory in Chile, with its sweeping wide-field camera, planned nightly monitoring to chart the comet's motion and brightness variations. Every subtle change in light could reveal rotation, jet activity, or even fragmentation. Meanwhile, the Very Large Telescope, VLT, also in Chile, and the Keck Observatory in Hawaii, prepared to capture high-resolution spectra. Their mission to dissect the chemical cocktail streaming from the nucleus and search for isotopic fingerprints that might betray the comet's birthplace in another star system. Space-based telescopes, free from the blurring effects of Earth's atmosphere, joined the effort. The James Webb Space Telescope, JWST, was perhaps the most eagerly anticipated player. Its infrared instruments, capable of detecting faint heat signatures, were ideal for probing the thermal properties of the comet's nucleus. Was it unusually cold as its sluggish outgassing suggested? Or had its dense body retained enough heat to shield volatile ices deep inside? Webb could also map the comet's dust particles, distinguishing between fine grains and larger chunks that shaped its unusual coma. The Hubble Space Telescope, though aging, still offered precise imaging to follow changes in the comet's tail structure, an important complement to ground-based tracking. But the excitement was not confined to professional astronomers. Amateur observers around the world prepared their telescopes, hoping to glimpse the comet as it brightened into visibility. For many, 3I Atlas was more than a scientific target. It was a cultural event. In the aftermath of its dramatic reemergence, 3I Atlas was no longer just a comet in the sky. It had become a puzzle piece for understanding how planetary systems form across the galaxy. Every observation, from the CME encounter to the Mars flyby and the December campaigns, added a layer of data that challenged existing theories. Its sheer mass suggested a far denser body than typical comets, while its chemistry seemed to carry signatures foreign to our solar system. For planetary scientists, this raised a tantalizing possibility. 3I Atlas might be the first physical sample, albeit remote, of material forged in an alien nursery light years away. One of the most profound implications lay in the comet's potential to test models of planetary ejection. Modern simulations suggest that most star systems, especially young ones, fling billions of icy and rocky bodies into interstellar space during their chaotic early years. If 3I Atlas truly originated elsewhere, then its presence here was a natural consequence of this process, a cosmic traveler on a trajectory millions of years in the making. But what made it unique was not just its journey, but its survival. How had such a massive object, exposed to the harsh emptiness of interstellar space, retained enough volatile ices to erupt when it neared our sun? Answering that question could reveal how common or rare, life-friendly, building blocks might be throughout the galaxy. The comet also sparked new conversations about exploration. Could future missions, perhaps launched on short notice, be redirected to intercept interstellar visitors? Concepts like NASA's proposed Comet, Interceptor, and ESA's F-class mission ideas suddenly seemed more urgent. These spacecraft, designed to wait in orbit until a suitable target appeared, might one day chase down another 3I Atlas, flying alongside to capture images, spectra, and even samples. Although no such mission was ready for this comet, its arrival served as a wake-up call. The universe would not send out invitations in advance. Humanity had to be prepared. Beyond the technical discussions, the comet resonated on a cultural level. For many, 3I Atlas symbolized connection, a reminder that our solar system is not isolated, but part of a larger galactic ecosystem. Just as meteorites on Earth can carry material from Mars or the asteroid belt, interstellar comets bring whispers from distant suns. To look at 3I Atlas through a telescope was, in a sense, to see across the gulf of light years, to witness matter born under another sky. In the end, the comet left behind more questions than answers. What star system had launched it on its journey? Was it once part of a larger body? Perhaps even a planetesimal that fractured during ejection? Could its chemistry hold evidence of prebiotic compounds that hint at universal pathways to life? While definitive answers may never come, the comet's visit deepened our sense of cosmic perspective. It reminded us that discovery is not just about finding certainty, but about expanding the boundaries of the possible. For now, 3I Atlas continues its voyage, drifting toward the outer solar system and, eventually, back into the interstellar dark. But its brief intersection with human awareness has left a permanent mark, both in the scientific record and in the imagination of everyone who looked up at the sky and realized we are not alone in the material history of the universe.